So for those of you listening to the podcast, I noticed the first few were pretty loud because the mic was sitting right underneath here. So I've moved the mic to right here. Let me know if it gets any better or worse. And I'll put the mic either back on where it was before or further away if it's still loud. And now I'm untethered, so I can come over here and do stuff like this. What?
I said, all right.
All right, right? Yeah, I feel free. Exam 1 is on Friday. It covers only the material that we covered in 1 and 2. So homeworks 1 and 2. The stuff that we are starting today, the energy balances, are not on exam 1. So don't worry about those for exam 1. There is not going to be any MATLAB code because, as we're about to find out, starting with the energy balances is where we really need MATLAB to make some progress because it's very rare, except in really, really simplified situations, that you can actually solve problems analytically. You also get a page of notes. You can write whatever you want by hand. You can write on the front and the back. I don't mind, whatever you want to do. I am going to ask you to turn in your notes page with your exam. So there'll be a stapler, and I'm going to have you staple your note sheet to the exam. Obviously, you can't use any of your phones. Your normal engineering calculators are fine. Yeah.
Will we get the exam? Will we get the page of notes back?
Yes, you'll get them back. And as noted in the syllabus, because we have 3 exams in here, there aren't any makeups. There's already a structure in place in the syllabus if you have to miss an exam or if you just bomb an exam so that you can drop your lowest exam score. So there aren't any makeups, but if an emergency comes up or something like that, please feel free to take care of it because that situation has already been accounted for in the syllabus, so you're not going to get punished just because something came up, right? That is already fit into the syllabus. Was there a hesitant question in the back? Yeah, what's up?
Is there any way you can put down a list of what sections you should read?
Yeah, so the sections that you can read, take a look at the first slide of each screencast on YouTube, and up there somewhere should be Fogler something, something, something. Those are the relevant sections.
Okay. And is there a way of relevant practice problems from the book?
Actually, the worked examples in the book itself, not the problems at the end, but the problems in the chapter, are really good.
Okay.
The reason they're really good is because you can actually work them by hand, because they're working them by hand. And if you need any code, they include the code right there. Their code is in a different piece of software called Polymath, but it's fairly straightforward to look at their Polymath code and say, oh, okay, that needs to go into MATLAB like such and such. But those are actually really good example problems. And in terms of what we're going to cover today and how it relates to homework 3, the equation, really this equation right here on the top for temperature as a function of time, that's the only new equation we're going to introduce, and we're going to apply that to all of the homework problems. So after today's lecture, or even if you're suitably motivated and now that you see that equation, you have enough information to do all of the homework problems. Almost everyone is going to require MATLAB because, as I said before, they're all coupled ordinary differential equations, and it's really hard to make any progress on those without something that can solve them for you. Any questions on anything up here before we get started with today's lecture? No? Okay. Feel free to ask more questions as we go, of course. So our topic today, the first 2 weeks we were talking mostly about material balances at a constant temperature. That doesn't happen very often because our reactions are usually exothermic. A constant temperature flame would be a very unusual piece of thing in front of you to hold your hand next to a flame and not feel any heat coming off of it. Most of our reactions are in fact isothermal, and most of our reactors tend to be either adiabatic, so if you remember adiabatic from thermo, that means we insulated it so that no energy can come in or out. Those are pretty common because they're really easy to build. You just wrap the thing in insulation. Similarly, I'd say, I don't really have a number on it. Equally often, we encounter reactors that have heat transfer involved with them, usually because if you let the reaction run by itself, it will overheat and either blow up or damage your equipment or damage your chemicals or something like that. There is a homework problem in here where I just want you to read an example in the book of a real-life example where something overheated and blew up. But it didn't blow up in a normal way. It didn't just like light on fire and an explosion happened. It was very specific to chemical reaction engineering and how that can go bad when you're dealing with thermal effects. So that is one of your homeworks that you have to deal with. Because we're only dealing with batch systems right now, our initial equation for an energy balance is going to look pretty simple, which is great. That's why we're starting this way. When we add flow to the system, we're actually going to use an equation that looks really, really similar to that. Not very much changes when we switch from flow, or switch from batch to flow. We'll hit that in a couple of weeks. But fortunately, they all look pretty close to that. If you're looking for equations in your book, this 9.2 is where they derive an expression like that. Your book loves to derive special cases of equations, and it can look like it's kind of overwhelming because there are so many special occasions or special situations. This is going to be the general form that we can always start with. If you're going to solve something in MATLAB, there's really no reason to simplify the equation any further than that, because MATLAB can do all that simplification for you as we go. So what you'll find me doing very frequently is starting off with this equation, or one that looks a little bit more complicated because it has x in there explicitly. But the power of having something like MATLAB or anything that can solve these differential equations relatively quickly is that we can start with the full differential equation and we don't have to make any kind of a significant attempt to simplify the thing before we can solve it. MATLAB doesn't care how many terms are there on the right-hand side. It will solve it all equally well. So the first thing that we're going to start off with, being that we're going to worry about energy, is the first law. And just like 100 and 102, we always have to start with a control volume. There's going to be some stuff in there. We're just going to say the entire body of reactants is the control volume. So if you're dealing with liquids, maybe the liquid height only goes up to here, but we're only talking about the liquid there. If it's a gas, then it's the entire volume of the reactor. And we deal with two types of energy. If the system is what's called closed, which is what we have, there can't be any mass going across our control volume boundary. But you can still have energy going across the system. So even though the system is closed, we're still allowed to have energy go back and forth. There are two types of energy that we're worried about in this class. And I'm going to draw these arrows in the direction of what's positive. So one of them is heat, which is a really bad word for energy, but that's what we call it historically. And we denote that as Q dot. The dot means that there's a rate, right? It's not just a kilojoule that was added, it's a kilojoule per second that was added. And if that is entering our control volume, then that's plus. I'm going to move my little CV there. The other one that we have is shaft work. And that comes from things like turbines. Those are usually pretty common. Turbines are usually attempting to take shaft work out of the system so that we can produce energy somewhere else. Or if you're dealing with something like a pump, you're trying to take shaft work and put it into the system so that it'll move a little bit further. And actually that W should have a dot on it as well. We tend to drop the dots most of the time when we're walking, or yeah, when we're walking we drop them. When we're writing them we drop the dots because they're always there. So if we want to do an energy balance on this system, any change in the energy of the system, so E_sys is the energy of the system, can only come from two places since it's closed. Any incremental change in heat, delta Q, minus any incremental change in work. For this particular, in almost all cases, there are, I think, like 2 problems in all of Fogler that deal with this situation where it's not true. We're going to neglect the work term. The work term usually comes in 2 components. One is the shaft work that we already saw before, and one is what's called flow work. The flow work term you would have gotten from 100. The flow work term for us goes away. Why? Because it's a batch reactor, right? It's one of the great reasons why we're starting with a batch reactor. We don't have to worry about the flow work right now. We will get back to the flow work once we get to the batch system. or sorry, to the flow systems. So there's no flow work because it's a batch. We're going to neglect shaft work because this is usually small. None of the reactors that we're going to deal with are designed to output shaft work. The only way that shaft work is typically introduced into a reactor is by a mixer. And unless your fluid is quite viscous, then shaft work is pretty small. When there's a particular class of compounds that are very viscous that need to be mixed, does anybody know what they are? We also have to, sorry?
Oil?
Yeah, oils are a good one. There's another one that we can make from oil. Very, very long molecules. Polymers. So when you react polymers in any kind of a reactor, you almost always have to mix them. Usually those are axial mixers, so they're very, very long so that we can control the temperature on them. But those are also exceptionally viscous fluids. And so there the shaft work can become quite significant. We're not going to worry about that right now. So that being the case, since we're ignoring shaft work, we get that the change in the energy of the system with respect to time is only dependent on the flow rate, well, not flow rate, the rate at which we are adding energy to the system. Those should all have dots on them. Just like we did in 100 or 102, I'm sure it came up in both of these, we have to come up with an expression for the energy of the system. This is usually where most of the complications come, in the sense that if you look at one book or one derivation, nobody uses the same terminology when they're talking about where all the energy comes from. It's usually pretty close. You can tell what one book is doing versus another book, and the end result is always the same regardless of what they start with. The energy of the system is equal to the sum of the moles of each component times the energy of each component. That's kind of a cop-out, right? The total is the sum of the parts. The energy of each part, E sub I, part being a species, a part is a component. So each component I has three components that represent its energy. There's an internal energy, which again is another cop-out. We're just saying all the other stuff that we can't measure is internal energy. There's a kinetic term, so the velocity of any component I, and then there's a potential energy term. These two are terms that you're going to get into in 101A. Those typically only become important when either things are changing velocity very, very quickly, so if they're going through valves or contractions or expansions or something like that. And then this GZI term, G is the gravitational constant and Z is the height of the species. Our reactors usually don't get more than a couple meters tall, so the change in potential energy is pretty tiny from the bottom of the reactor to the top of the reactor. These tend to only become important, the GZI, when you're talking about tens or more meters, especially in comparison to the U sub I term. So the U sub I term tends to be much, much greater than V sub I, the kinetic energy term, and GZI, the potential energy term. So we're going to neglect those two terms. You can add them back in there, they just don't do very much. And you'll see what that means, how that changes the energy balance when you get to 101C. We include stuff like that, or 101A. So therefore, this becomes approximately equal to the total number of moles of each species I times the potential energy of each species. Sorry, internal energy. See what happens? Because in 101A, we use U for velocity and not V. We also use U for internal energy there, too. And then if we, actually, I'll just go on to the next page for that because it's not going to have enough space there. If we use a little bit of our thermo knowledge, we can relate this internal energy to the enthalpy of each system. So I will just write that underneath here because this is what I'm about to write on the next page. If we write enthalpy is equal to internal energy plus PV, right? If each one of those have subscripts i's on them. Again, we're going to only deal with systems that do not encounter phase change. So that's the only version of enthalpy we have to use. We're going to take this value of U and stick it inside this sum. Such that the energy of the system is equal to the sum of the moles of each component times the enthalpy of each component, or enthalpy, if that's your thing, minus PVI. Again, because this is a closed system and not a flow system, we have another nice simplification that we have here, which is that any product PV tends to be much, much less than any product of HI. Again, that will change when we switch over to a flow system, but for now we don't really have to worry about the PV term. Flow systems, it'll get naturally incorporated in there, and we'll see how that happens later. So the final result that we have is that for a closed system, for a batch system, the energy of the system is approximately equal to the moles of each component times their enthalpies. Which makes things a little bit easier when we talk about, we can take a derivative of this term, right? We can apply our good friend the chain rule to this. So the chain rule says, you know, the derivative of the product is the first times derivative of the second plus the second times derivative of the first. So the rate of change of energy in the system, dE dt, is going to be equal to the sum of the moles of I times the derivative of the first one, or second one, which is dHI dt, plus the sum of the enthalpies times the derivative of the moles of each one. And remember, this is then going to be equal to Q dot. So we didn't do anything there except chain rule. Now we do need two little bits of thermo. One from thermo was a definition we had, which was the change in enthalpy with respect to temperature at constant pressure. This was no derivation that we made. This was just a definition. That was the heat capacity of species I. And so that means we can replace this dHI dt term with a heat capacity of I times the change in temperature with time. So that's one of the simplifications we're going to make. That's going to be these two. So this term is eventually going to go in here. And we get that, it's not really a simplification, it does make our life easier, so I guess since that's the definition of a simplification, that's a simplification. And then the other thing we're going to do is replace this dNi dt term. And that one's going to come from a material balance. So remember the change in moles of species I with respect to time we saw was equal to the rate of either generation or consumption of I times the volume, which is also equal to minus the stoichiometric coefficient of I times the rate of consumption of A times volume. Right here we're using our stoichiometry, which basically look like this. All right, so the top one, this one is from thermo. So I'll just say that's from 102. And this one, I don't know, you could call it from 100, but that's more like from week 1. Right, we're going to put our material balance inside here such that this term here is going to go up here. Right, so we've simplified those two terms. Simplified them in the sense that we have expressed them in terms of something either that we can measure or something we're interested in. Whether that be the rates down here of A, because we normally write our elemental balances our species balances in terms of whatever species A is, and this one from thermodynamics because we have tabulated values for heat capacities, although they can occasionally look somewhat nasty. So if you plug all of those in, and there's not much other than algebra in order to do this, you get that equation that we had shown on the very first slide, which is that the change in temperature with time is equal to however much energy you're dumping into the system plus delta H times R sub A V divided by the sum of the moles of any species times its heat capacity. And of course that has to have some sort of an initial condition, which is going to be some kind of a temperature. So the reactor or the inlet to the reactor, in our case the initial temperature of the reactor will always start as something, and we need to know what that something is. So this is our energy balance for a batch system. And that's pretty much the only one that we're going to deal with for batch systems. When we come back to multiple component or multiple reactions next week, we're going to have to revisit a couple of these terms because there's more than one reaction going on, but the general structure will look just like this. So this one was specific to one reaction. Some of the other assumptions that we made along the way was that there was no shaft work, and there was no phase change. This one also requires constant volume. Yeah?
Do we assume speed is constant during the process?
Sometimes. Yeah, sometimes. Typically, this has to be coupled with our other differential equation. It's usually not enough to solve anything of particular interest just by knowing how the temperature changes with time. Because the other thing that's changing in time, there are two other things. One is the moles of any component. That's also a function of time. And because that is a function of time, your rate also tends to be a function of time. So these two tend to be functions of time. And then, as was just pointed out a minute ago, the question comes to heat capacity as to whether or not we're going to keep that constant or look at it as a function of temperature. In general, this is a function of temperature. We're going to see that in most cases we'll keep it constant, but there are a few times where you need to account for temperature. And then I can't sketch it in here because I'm out of space for arrows and I'm not going to do the drag and drop thing. This delta H term is also a function of temperature. Right? That delta H term is always evaluated at whatever the temperature of the reaction is. So I'll sketch that in just a little note over here. Delta H is the delta H of whatever temperature you're at. And we're going to see, is there any reason why I can't just tell you right now? No, I can just tell you right now. The adjustment that we have for the enthalpy of reaction is derived from this thermodynamic relationship in the middle here, the heat capacities, this one. Right? We can apply that same relationship to the enthalpy of reaction and get that any enthalpy of reaction, delta H, is equal to some delta H, usually with a circle on it, to say if we knew it at some reference temperature under some reference condition, we can take that delta H and add to it a new term which is delta Cp times T minus Tr, where R is your reference temperature, right? At whatever temperature you know H circle, that's the R that goes in here. So we see that delta H tends to be be a function of temperature. There will be several cases where in a homework I will just tell you, assume that delta H is constant, which makes life a little bit easier because you just put a single delta H in there and then you never worry about it afterwards. Delta H will be constant also if the delta Cp is either 0 or very close to 0. Sometimes the products look very, very similar to the reactants, so we neglect delta Cp that way. For example, if you're isomerizing something, the heat capacities of isomers are typically very, very similar, so we wouldn't account for Cp there. Or if you're dealing with very small temperature changes, that whole delta Cp times T minus Tr is negligible. That one usually doesn't happen quite as often. So we have this delta Cp term here, which it depends on how you're dealing with your heat capacities. The heat capacities that we dealt with in, you probably would have seen the heat capacities like this in 102. But I think you definitely would have seen them in 100. Usually Cp looks something like A plus B times temperature plus C times temperature squared plus D times temperature to the third. That last term sometimes changes. Maybe it's 1 over T or something like that. That's the general form. If you go look at your EQ Calc spreadsheet, you've got tons and tons of relationships for Cp for lots of different components in that particular form. But this, I mean, for lack of a better word, this kind of expression sucks. Right? If we have to plug in C sub p as a third order polynomial inside there, and you've got one for every component, that's a ton of Cp parameters to carry around. Right? If you just have 2 species as reactant and 2 as product, you now have 16 of those Cp terms that you have to carry around. It's a pain in the neck. It's really easy to do if you've got MATLAB. You code them in once and you're done, and MATLAB will carry them around perfectly every time. But if we ever need to make any kind of progress by hand, or if we just want to see general effects without these Cp terms, usually we will take C sub p and approximate it as the heat capacity at the initial temperature. And that one's usually a little bit better. Right, that's something, at least we only have to calculate it once. And then we assume it's constant after that, right? We calculate it at T naught and assume it's always that heat capacity at T naught. If you're going to do it by hand, or if you're doing it for a general reaction like we might have on a homework or an exam, where it's just A plus B goes to C, those heat capacities are always going to be constant. In your project, you'll have to deal with non-constant heat capacities, but it's really not that bad. You find those coefficients and stick them in there, and then you're done. This particular simplification over here of a constant heat capacity evaluated at some temperature allows us to simplify this bottom term. And I'm sure you guys love how colorful this is getting at that point. This term ends up looking a little bit more simple because now our heat capacities are constant. And in fact, we can express this now in terms of conversion x, which is helpful when we have a single reaction. When we get to multiple reactions, we can't really go any further than this because we typically don't define conversions when we have a multiple reaction system. But if we only have a single reaction, we can write this whole dt expression as a function of x, x being the conversion of a species. And that can be a little bit more helpful when we're really only interested in one reaction and we want to talk about its conversion. In order to do that, that sum term, the sum of n sub I times the heat capacity of I, remember that's going to be evaluated at T naught, is going to be equal to the sum of the heat capacities of I at T naught. And now we plug in our expression for the moles of any component as a function of conversion, which is the moles of A times the theta A plus the stoichiometric coefficient of whatever that is times the conversion of A. And we can get that, we generally, again, this is one of those simplifications that your book makes that's not really a simplification. It doesn't really help you solve the problem at all. It just separates the parameters into 2 separate numbers, which I guess some people would assume is simpler. I think it makes the equation look more difficult to solve, but it does give us a couple of numbers that we can calculate along the way. We can factor out that Na0, and then we have two terms on the inside, which is a sum of theta I Cpi, which again, that term is easy enough to evaluate from initial conditions, right? The theta I is the initial moles of something over the moles of A, and the Cpi, as we're going to make for this assumption we're going to make for most of our problems, is constant at some initial temperature. So we can calculate that sum of theta I Cpi just from initial conditions, and then we've got a sum, what's that look like? A nu sub I times C sub pi times xa. This term sums of anything times its stoichiometric coefficient. Remember we saw before that anytime we have one of those, it's defined as a delta. So if we wanted a delta H of a reaction, it's the stoichiometric coefficient times the enthalpy of I. Gibbs energy was stoichiometric coefficient times G, etc., etc. Yeah?
Is conversion included in that sum term?
Well, there's only one conversion. So conveniently, we can pull that conversion out because it's the same conversion for all of those sum terms, which is one of the reasons why this only works for a single component system, because if it were a multi-reaction system, now you have more than one conversion. So there's not really any reason to talk about conversion in those cases. This parameter you'll see often referred to as delta Cp. It's the stoichiometric coefficient of each term, each component multiplied by its heat capacity. So if you tried to put all of that together into our energy balance, you'll come up with the equation that you see pretty frequently in the book, which is a decent starting place because it's nice in the sense that it shows you how the temperature dependence of each term behaves. So you've got first a Q dot plus your enthalpy term. So you've got a delta H circle plus delta Cp times T minus Tr. Right, that is delta H at any temperature. It's just we've spread that out a little bit so that you remember where it's going. All right, I assume you gave yourself more room, so I'm going to move that down a little bit. And then the other term didn't change a lot. It's still Ra times V. But remember, your rate of reaction also depends on X, right? Because it's got concentration terms sitting inside there. And then all of that over this new term that we have, which is Na0 times the sum of theta I Cpi plus delta Cp times Xa. Right, that's the same equation that we saw before. It's just now we've been a little bit more explicit with where conversion comes in, which is here, and a little bit more explicit where temperature comes in, which is here. But for some odd reason, we always stop here because that's about the most complicated equation that we want to write. If we wanted to really completely express dt as a function of time, we would have to plug in our expression for Ra, which depending on the reaction can be rather complicated. We would also need expressions for delta Cp, which you can see would be pretty nasty if we had a 4-parameter term for Cp, but most of our Cp's are going to be a single value. Yeah?
Is V the molar volume or the total volume?
Total volume. Volume of the reactor in this case. For today's lecture, we're going to make not really a simplification. If we say that something is adiabatic, then Q is 0. If we do have thermal effects that we'll see on Wednesday, like if we dunk a heat exchanger in there and try to cool the reactor down as it's running, that's only going to come into the Q parameter. If the system is adiabatic, there's no heat exchange with the outside world, then Q will be equal to 0 and we won't have to worry about that Q term. So this would end up going away. This tends to have to be coupled with the other ODE that we have. You could write multiple ODEs for each species. Because we only have a single reaction here, we only typically write the ODE that represents conversion as a function of time, which just starts off as the ODE of species A, and then we substitute the definition of conversion, and then end up getting this, which you would have written on your homework. dxa dt is equal to minus r sub a over na naught times v, which, if the volume is constant, simplifies to ra over ca naught. All right, so generally we have to solve these two ODEs. We have to solve this one and this one at the same time, because they're both dependent on terms that show up in the other one. There's a temperature dependence inside Ra in two pieces. What are the two temperature dependencies of Ra? They're both Ks. So which two Ks do we have?
K naught and K1.
K naught and K1. Are you referring to equilibrium K or rate K?
The one that I'm referring to the one that gets us to KSC.
Yes, so those are equilibrium Ks. So those are the big capital Ks. So R sub A depends on temperature in two ways. First, because the equilibrium K, K of T, depends on temperature. And then what's this K? Lowercase k. That's our rate constant, right? That's our Arrhenius expression for temperature, goes in there. So that's an exponential dependence on temperature as well. So both of these tend to be quite strong functions of temperature. Which means if this is a function of that, so if the ODE for x is a function of the ODE for temperature, and the function of temperature is evidently a function of the ODE for x as well as it is here, those are coupled. There's no way to solve this one first and then solve that one, or solve that one first and then solve this one. They have to be solved at the same time. Which is why MATLAB becomes our friend here, because we don't really have any way to do this without a computer to help us. There's no good way to do that. But that should be a good thing, right? Because we have computers that can do that for us now. Your calculators can do this. There is one simplification that you can make that we're never going to use until we get to a flow system, but it's easy enough to identify now. You can substitute one of these into the other one and make a little bit of progress on it, but you still end up with now an ODE and another function that you have to solve at the same time. But it does result in something that's we will see to be interesting later. If you look in your book, if you look in Fogler for an expression of x sub a as a function of temperature, or temperature as a function of conversion, and this one is equation 9-16, and this one is 9-17. I'm only going to mention one because it's the only one that we're interested in. And these are for adiabatic systems. So for Q is equal to 0. Q equals 0 becomes a limiting case that we'll see for flow reactors, and this relationship does help. If you want to see the full derivation for this, it's available in one of their appendices. It's pretty lengthy. You can get that the conversion is equal to the heat capacity of I times T minus whatever your reference temperature is, sorry, your initial temperature, over your enthalpy. Right, we haven't helped an enormous amount. You still have to put that back into the other ODE and solve it. This does have an advantage, though, because it predicts the following. If you have temperature and you want to plot conversion, if you let delta H be approximately constant and your CPI be approximately constant, then the plot that you get as a result is a straight line for Q is equal to 0. And why is that useful? It's not particularly useful for a batch adiabatic reactor. It is exceptionally useful when you have flow reactors because this gives us a way to not only size a reactor, but decide how many reactors we need and what kind of cooling we need in between those reactors and what the temperatures should be. Unfortunately, it's not a plot that we're going to get to until about week 8. But I want to bring it up now just so that when you see it again and I can say, you saw this before, you can feel a little bit worse about not remembering this. But that's the only time that's going to come out. It is approximately constant, though, as temperature goes up for an adiabatic reactor. So the general solution procedure, actually, we're not going to have enough time to get to that example today, but that's okay. We were only going to finish that example next week, anyway, Wednesday anyway. When you're calculating rate constants K as a function of temperature, there's no shortcut version for that expression, right? We always have to use the Arrhenius expression in order to figure out what the K's are. If you ever need to calculate equilibrium coefficients, it's okay to get started with the full version of KEQ. So we would say that KEQ is equal to K0, K1, K2. It's fine to get started there. But as you saw in the expressions that we had, particularly for K2, that's a fairly nasty expression for temperature. So it's okay to start there. Every time after that, once you say, okay, I know what KEQ is at a particular temperature, maybe it's 298, maybe it's 400, whatever that temperature happens to be, for every temperature after that, we're only going to use the shortcut version of K. We're never going to try to put K0, K1, K2 into any of our differentials for temperature. It's not that we don't know the expressions for them, it's just a pain in the neck to carry them around. So every time that we want K at any function of any temperature, we're always going to approximate this as the shortcut K, which means we can calculate our K at some reference condition, R. Right, so here KR is probably going to be KEQ, unless I just happen to give you a KR. Some K at some particular reference, times that K1 term. I need more than that. Times the exponential of minus delta H divided by R times 1 over T minus 1 over TR. So I mentioned this equation a few times when we were dealing with equilibrium constants, which is that if you just know K at any temperature, you can get the shortcut approximation by just multiplying by K1. Where you get that first K from depends on what your problem looks like. If it's a problem with real components, things for which you can look up Gibbs free energies of formation, then you can just calculate this K0 or the full KEQ and put it in there. It's up to you how you want to do it. Either one will end up working because that scaling is still hold. Or I could just give you K is equal to like 3 at some temperature, and then you would put 3 in here, and whatever that some temperature is over here. But this is as far as we're ever going to take the equilibrium coefficient, or equilibrium constant, when we're dealing with thermal effects inside a reactor. The only difference is whether or not I get Kr from an actual Gibbs energy of reaction calculation, or you're just given Kr as some number. Either one is doable. There is a little catch to this, which is don't forget that this delta H, this is a function of temperature. So it's tempting to just put in a constant delta H right there. If delta H really is constant, so if you look at that handout that I gave you, I only give you a delta H at a particular temperature, so you would imply that that delta H is not constant. If delta H is constant, the word constant will show up right next to it. If delta H really is constant, then this becomes a fairly straightforward calculation. Otherwise, you need to put the delta H as a function of temperature. All right, so we've only got about 3 minutes left, so I'm not going to try to start that example because that example is going to require MATLAB to do. So if you haven't turned in your homework, the homework drop box is up here. Where are the stacks of homework? If you have those stacks, please bring them back up to me. And if you have any extra handouts, the little cutouts, please bring those back to me as well. And I will see you in here on Wednesday. Homework 3 should have been posted by now, too.